Welcome to another video from Lockdown Electronics with me, Bill, and we've got another one in our electronic building block series, and this is about the bipolar junction transistor. So let's start by having a quick look exactly what the bipolar junction transistor actually is. The bipolar junction transistor then is a semiconductor device, originally made from germanium, but now more likely to be silicon, although germanium transistors certainly still do exist. It's called bipolar because its operation is governed by both electrons and holes. Now, electrons are atomic particles with a negative charge. Holes are slightly more conceptually difficult to understand. They're not a positron. They are a place in the crystal lattice or the atom where an electron could exist and will appear to have a net positive charge because of the positive charge of the nuclei of the atom. Well beyond the scope of what I'm going to talk about today, but it's just easier to call them electrons and holes and think of the electrons as being negative and the holes as being positive. It's a junction transistor because the action occurs at the interface of two types of semiconductor, that's the N and the P type, created by applying different types of doping material to the silicon or the germanium or whatever the semiconductor material is. Invented in 1947 at the Bell Telephone Labs by John Bardeen and Walter Britton, under the direction of William Shockey, and obviously a pivotal moment in science. Transistor operation is complex. Now, if when you've watched this video you're still confused, first of all, I'm sorry. But secondly, you're in good company. Here's a couple of quotes. Kaplan and White, which is most definitely both university textbooks actually, say that why and how a transistor works is a bit subtle and can easily confuse the beginning student, and the way an NPN transistor amplifies current is quite complicated and rather difficult to understand. So I think when university level textbooks are saying that to you, then I think it's fair cop if you're a bit confused. Don't worry, you're in good company. Indeed, one of those books goes on to suggest that you should get other texts and read their description of how transistors work, so that you can fully understand it. And maybe I should say the same. There's plenty of videos on YouTube about how transistors work in detail. Some of them for me make more sense than others, but I'd encourage you, if you're interested, to shop around. However, that doesn't you don't need to worry about that if you just want to use them. Essentially, a small change in base emitter voltage results in a large change in collector current. I think that's probably the key thing. And the ratio of base to collector current is called the beta or beta, or sometimes the HFE. In other words, it's an indication of the gain or the amplification factor of the transistor. Okay, let's look in a bit more detail at transistors then. There's two types, NPN and PNP. They have those symbols. You need to perhaps find your own way of recognizing them. NPN does tend to be more common than PNP, but that's a bit of a generalization. I remember it by remembering that PNP, PN points in. That's how I remember them. So the NPN arrow is pointing out. This video is going to focus on the NPN transistor. I think if I try and do both, it'll be confusing. It's confusing enough for me, and I'll probably confuse you further. It's constructed from three semiconductor regions. The NPN there you can see. So there's the emitter, the base and the collector, and I've chosen the shading of colour there to try and emphasize how much doping has been applied to each region. So the emitter is quite heavily doped in the darker blue. The base is lightly doped P-type material, and the collector is less heavily doped N-type material. They're often described as two diodes back to back, and here's the analogy, and I can see why they might say that, because you have got two PN junctions. I'm not entirely convinced that's always the best analogy, so we'll look at that in a while. Transistors are current amplifiers, so let's go and look on the bench. This is quite enough theory for right now. Let's go and look on the bench first of all at how the two diode model plays out, and then have a look at how transistors operate as current amplifiers, and then we'll look at how the small change in voltage can result in a large change in collector current. Okay, I'm going to start by just having a look at the two diodes analogy, because it is valuable but not always. So what I've got here in my component tester are two silicon diodes, and I've got them carefully threaded into connections 1, 2 and 3, and I've got them configured to look like an NPN transistor. So let's see what the tester makes of that, and hopefully you can see that. I'm just going to, yeah, hopefully you can see that reasonably well. It's not fooled at all. It said it's got two diodes, and it's giving me forward voltages of 0.69 in both directions for those two silicon diodes. So it's not fooled at all by that. It doesn't think that's a transistor. Okay, we'll remove those two. Now here is an NPN transistor. So first thing we're going to do is I'm going to just connect base, if I can do it without making an accidental connection elsewhere. I'm just going to connect base and collector and see what we come up with here. Yeah, and that's saying it's a diode. It's even giving me its capacitance. So base and collector are a diode. Let's now try base and emitter. They should also be a diode. Let's just try and get them in there. Do a test again. And yeah, it's come up as diode yet again. So now what we'll do is we'll put all three wires into it and see what it makes of it now. Having messed about with the legs, it's not playing terribly well. Okay, let's put the test on again, and it's got a very different result now. It's saying it's a bipolar junction transistor, NPN, collector on pin 1, base on pin 2, emitter on pin 3. So there's one of the reasons why the double diode analogy doesn't always work. Just before we look at the current amplifying properties of a transistor, just a little point to make. Earlier I showed you this diagram about the three regions of a transistor, and if you were being really eagle-eyed in that last video, you may have noticed that the emitter to base capacitance was being measured by my tester as 56 picofarads, and the base to collector capacitance was 258 picofarads. That's quite a sizable difference, really, and certainly my interpretation of that is that it's evidence of something that looks a bit like this, because a bipolar transistor isn't actually a symmetrical device. The collector is much larger, and if you visualize there the area of contact between the emitter and the base versus the area of contact between the base and the collector collector interface is much larger, and remember that would be in 3 dimensions. We're just seeing it in 2 there, and my interpretation of those differences in capacitance quite simply is there's a much larger area between base and collector, which would result in a larger capacitance. That's maybe not the whole story, but that certainly for me is a useful explanation. Okay, let's now go and have a look at the transistor as a current amplifier and the effect of base voltage on collector current. Here's the setup then to have a look at the transistor operating as a current amplifier. So what we've got here is an NPN transistor. This is one with a yellow band, and we've got it wired in what effectively is common emitter configuration. The emitter connected to the negative supply directly. The collector is connected to the positive supply via a 1K resistor to act as a load to stop any damage occurring, and This meter is measuring the collector current, so the current from the collector to the positive rail through that 1K resistor. The base of the transistor is connected via this potentiometer here to allow me to control the base current, and this meter is measuring the base current, and currently, as you can see, it's 0. In fact, they're both 0, so the transistor is most definitely not conducting. So just to make you aware, that is milliamps and that is also milliamps, and that'll become significant in a moment. So I'm now going to increase the base current very slightly. This is quite a fussy control, so I'm just going to do it very gently, and as we start to get some conduction, so there is 0.002 milliamps, yeah, so if you like, it's 200 microamps, and we're getting 0.1 milliamps of collector current. So that's the point at which the transistor starts to conduct. So if I now advance that, as you can see, the collector current is increasing quite rapidly, and by the time I've reached about 0.04 milliamps, well, that's 0.06, it's good, but it's good enough for what we're now at 4.7 milliamps collector current. So we're still at 0.06 here, and if we continue, we never get, even as we approach half a milliamp base current, we're at 4.9 collector current, and no matter how far I go now, it probably won't go any higher because I'm just using a 5-volt supply. But the point I'm trying to make here is there's clearly a point at which the transistor doesn't amplify anymore. So as I come back down now, we're still at 4.8, and it doesn't start to drop until the base current is below about 0.05 milliamps. Now, try and make sense of this. I've graphed that for every 0.01 milliamps, so I'll show you that graph in a moment. So I'm just going to turn that transistor off. So that's the blue one, sorry, that's the yellow one. This is the blue one. Again, it's an NPN transistor, so I just pop that in circuit, and let's now do the same sort of thing. So we're going to advance it till we get some collector current, just doing it very slowly. Oops. Right, 0.001 doesn't make any difference to collector current at all. Now the collector current started at 0.001, where we've got 0.2 milliamps collector current, and very rapidly now, as we approach 0.01 milliamps, we've got nearly 2 milliamps of collector current, so that's risen really sharply, more than the other one. And if I continue now, we're at about, let's just see if we can get to a similar level for you. There's 0.45, and we're at 0.02 milliamps, so that has actually required even less base current to achieve pretty much the peak of the collector current. Again, I've graphed that, so let's now go and have a look at those graphs and see what we can say about those two transistors, the yellow and the blue. Let's have a look at the results then of the measurements I was making as the transistor as a current amplifier. So first of all, the transistor with the yellow mark, and here is a graph. The blue trace along the bottom is the base current, and the brown trace rising rather steeply is the collector current. Scale on the left is in milliamps, so you can see that very small changes in base current have led to a very large change in collector current. Now if we look at the ratio on the sort of the center of that rising curve, the ratio is approximately 70 to 80 times. So the collector current is about 70 or 80 times greater than the collector current. And if we put that transistor into the multimeter and test its HFE, you can see we get a result there of about 70 for HFE. which fits with our measurements there made on the breadboard. So that's the example. So the beta of the yellow transistor then, or the HFE, is about 70. On then to the blue transistor, and the blue transistor, as you can see, the base current along the bottom in blue still rising at the same level. Collector current rises, if anything, even more steeply than the yellow transistor, so it's clearly a different level of performance. So again, if we take the sort of the midpoint of the rising curve, the ratio there is approximately 160 to 180, and if we check the HFE, comes out as about 165. So you can see those two NPN transistors both have quite different HFEs or betas, and the gain is quite different. And you can certainly have gains larger than that as well. Okay, you've hopefully seen there then that large change in collector current is influenced by a minute change in base current. Okay, so I'm back with the yellow transistor, and the base current and collector current arrangement is exactly as before. I've now got a third meter here, and this meter is measuring the voltage on the base, and currently we're most definitely off, no current flowing and negligible voltage, 0.001. It's probably inside the measurement error of my rather ancient fluke. So what I'm now going to do is I'm going to start increasing the base current, and first thing to notice, still no base current, but now we're at 0.45 volts, and we're just starting to get 0.001 milliamps base current, but still no collector current, and we're at 0.447 volts. So the transistor is still switched off. So if I now slowly advance that, as I approach 0.5 volts, as close as I can, very little change in base current, and the transistor is most definitely still off. There is zero collector current. I'm going to go up to about 0.55 now if I can. Right, there's, well, 0.56 let's say, and collector current's increased slightly, but still no measurable collector current. But then as we approach point, suddenly we start to see at about 0.57 there, we start to see some collector current, and by the time we reach 0.6 volts we've got a little bit more base current, and we've definitely got some collector current now. So let's now continue to increase that, and when I reach about, there we go, that's about the maximum collector current we're going to get, and you can see the base voltage is now 0.672. So the difference between the transistor being off completely and on is about 0.2 volts, and hopefully that's an example of how important the bias voltage is when you're designing an amplifier. And I'm just going to switch that all off, and we'll just swap onto the blue transistor just to convince you that its characteristics are going to be similar. So that's the blue transistor in position. So no current, no volts, so I'm going to increase it as best I can without getting too keen on this control. I'm going to go up to about 0.45 volts. So there's 0.45 volts, just beginning to get a hint of base current, but still no measurable collector current. Starting to get some collector current now at just over 0.5 volts base voltage, and as I approach 0.6 volts we've got 4.8 volts collector current, and I'm sure it's not passed you by that 0.6 volts is about the threshold voltage for a silicon PN junction. So what we've done is we've now moved the emitter to base junction into conduction, because we've reached the point in voltage where it's now properly forward biased and is able to conduct. And we've got 0.04 milliamps. Oops, that's the meter deciding to it's had enough for timeout, and we've got the full amount of collector current. Okay, so here I've got the fluke set up in diode test mode, continuity if you like, and I've got one of the connections attached to the base. So I'm now going to just go to the collector, and that's telling me about 0.64 volts is the forward voltage across that those two legs of the transistor. In other words, it's a diode. If I swap those over, you should get 0. If we don't, we've got a problem. Yep, so there you go, that's absolutely not conducting. And then if we go to the base emitter junction, apologies you can't see terribly well, it's so small. The base emitter junction, we're getting 0.646 forward voltage, and if I swap that over the way around, we should get 0. Indeed we do. So that's behaving, the base emitter junction and the base collector junction are behaving like diodes in that case, and that's where that double diode analogy does work. Well, I hope your head isn't spinning too much after all that detail. I think the key points to take away from the video are, firstly, transistor operation is complex, and if you don't fully understand it, you're in good company. I don't think you do need to fully understand what's going on at the atomic particle level to be able to use transistors effectively. You've hopefully seen the key characteristic of a bipolar junction transistor, which is that of a current amplifier, and you've hopefully seen the gain, that the change in base voltage can be quite small, but the change in collector voltage is a great deal larger. And we've also seen that the forward bias voltage of the base to emitter junction is key to triggering that amplification, and hopefully therefore there's a salient point there that's getting the bias voltage right is clearly very important for effective and linear transistor operation. Hope it's made some sense. Hope I've not confused you. Thumbs up if you've liked it. If not, you can click the thumbs down. Be great if you could let folk know about the channel, and also consider subscribing if you haven't already. Thanks very much for watching. See you on the next one.